Imagine a place in the vast expanse of space, a place where gravity is so incredibly strong, so powerful in fact that nothing can escape its grasp. Not even light, the fastest thing in the entire universe. This extraordinary cosmic object is what we call a black hole. They challenge our understanding of physics itself. They beckon us to explore the very limits of what we know about the cosmos. Black holes are not empty spaces, as their name might suggest. They are actually an enormous amount of matter. This matter has been squeezed into an incredibly tiny area. Think of a star many times more massive than our own sun. When such a giant star reaches the end of its life, it can collapse under its own immense gravity. This catastrophic collapse can lead to the birth of a black hole. All that mass, all that material is compressed down into a point of infinite density, or so our theories suggest. It creates a gravitational field so intense that it warps space and time around it. The defining feature of a black hole is this overwhelming gravitational pull. It's like a cosmic vacuum cleaner, but infinitely more powerful. They are truly one of the universe's grandest enigmas waiting to be unravelled. We all experience gravity every single day. It's the force that keeps our feet firmly planted on the ground. It's what makes an apple fall from a tree. It's the invisible tether that holds the moon in orbit around the Earth, and the Earth in orbit around the sun. Gravity is one of the fundamental forces of nature. It governs how objects with mass attract each other. Without gravity, planets would not form, stars would not shine, and galaxies would not hold together. Now imagine that familiar force of gravity, but amplified billions upon billions of times. That's the kind of gravity we are talking about when we discuss black holes. These objects are the ultimate heavyweights of the universe. They have so much mass packed into such a small volume that their gravitational pull becomes overwhelmingly dominant. This extreme gravity is not just strong, it fundamentally alters the fabric of space and time in its vicinity. It creates a deep well in space-time, so deep that it's almost impossible to climb out of. For a black hole, the escape velocity at a certain point becomes greater than the speed of light, and since nothing can travel faster than light, nothing can escape. This incredible, inescapable gravity is the very essence of a black hole. Light is our primary way of observing the universe. We see stars because they emit light. We see planets because they reflect sunlight. Light travels incredibly fast, at nearly 300,000 kilometers every second. It's the cosmic speed champion, the fastest thing there is. When light from an object reaches our eyes or our telescopes, we can perceive that object. Its color, its brightness, its shape, all are revealed by the light it sends our way. Without light, our universe would be an invisible realm, a dark and silent stage. For us to see something, it generally needs to do one of two things. It either has to produce its own light, like our sun or a distant star, or it needs to reflect light from another source, like the moon reflecting sunlight. If an object neither emits nor reflects light towards us, it will appear dark or even completely black. As we've discussed, the gravitational pull near a black hole is so immense that its escape velocity exceeds the speed of light. This means that even light itself, despite its incredible speed, cannot escape once it crosses a certain boundary. This is the simple yet profound reason why black holes appear black to us. When we talk about a black hole and its ability to trap light, there's a crucial concept we need to understand. This concept is known as the event horizon. You can think of the event horizon as the black hole's ultimate boundary. It's not a physical surface that you could touch, like the ground beneath your feet. Instead, it's an invisible line drawn in space. It marks the point of no return. Once you cross this line and enter the region within, your fate is sealed. There is no going back, no matter how powerful your spaceship. Imagine sailing a boat towards a giant cosmic waterfall. The event horizon is like the very edge of that waterfall. As you get closer, the current gets stronger and stronger. You can still turn back if you're far enough away. But once you drift over that edge, you are inevitably going down. For a black hole, the current is its immense gravity, and the waterfall is the black hole itself. The event horizon is that critical point where the gravitational pull becomes so overwhelmingly strong that escape is impossible, even for light. Anything that crosses the event horizon is pulled inexorably towards the black hole's centre. Section 5. A universe of colour. What if black holes weren't black? We've established why black holes are black. Their gravity is so strong that light cannot escape from beyond the event horizon. This makes perfect sense according to our current understanding of physics, particularly Einstein's theory of general relativity. But now, let's engage in a bit of scientific imagination. Let's ask a wonderfully curious question. What if black holes weren't black? What if, instead of being voids of darkness, they shimmered with brilliant colours? This is a delightful thought experiment that can lead us to ponder the universe in new ways. Picture it for a moment. Imagine peering through a powerful telescope. Instead of searching for the subtle gravitational effects of an invisible object, you see a vibrant spectacle, perhaps a colossal black hole glowing with an intense fiery red. Or maybe another one, smaller but spinning rapidly, emitting a cool, ethereal blue light. You might even see some that shift colours or display a whole spectrum, like a cosmic rainbow. This idea, of course, goes against what we currently know. For a black hole to have colour, light would somehow have to escape it or be generated at its edge in a way that carries specific colour information. Section 6. Reading the rainbow. What could coloured black holes tell us? If we were to discover that black holes came in a variety of colours, the first question scientists would ask is, what do these colours mean? A crimson-red black hole, for example, might hint at something very different from an emerald-green one. Perhaps the colour could be related to the black hole's temperature, but this is a tricky concept for black holes. Stephen Hawking famously predicted that black holes emit a faint radiation, known as Hawking radiation, which is related to their temperature. Could this radiation, if much stronger and in the visible spectrum, manifest as colour? Another possibility is that the colour could tell us about the material the black hole is currently consuming. Black holes are often surrounded by accretion disks, vast swirling platters of gas, dust and stellar debris that are being pulled inwards. As this material spirals towards the event horizon, it heats up immensely due to friction and gravitational forces, causing it to glow brightly. Perhaps different elements or compounds in this infalling matter could produce specific colours as they are energized, painting the black hole's vicinity with their spectral signatures. A black hole feasting on hydrogen might glow one colour, while one consuming helium might glow another. What if the colour was linked to a black hole's age or its spin? A young, recently formed black hole might blaze with a brilliant, energetic colour like a vibrant violet. An ancient black hole, having consumed much of its surroundings, might fade to a dimmer, more subdued hue, perhaps a deep indigo. Section 7, A New Cosmic Canvas. How Colours Would Change Our View. The discovery of coloured black holes would send vibrant waves throughout our understanding of the cosmos. Our view of the universe, currently punctuated by dark voids, would transform into a dynamic and colourful tapestry. Imagine astronomical images showing the distinct glows of these massive gravitational entities. Space would seem more alive, more visually expressive, with these new points of light and colour. Our fundamental theories of physics would face an immense challenge. For light to escape a black hole and present itself as colour, our understanding of general relativity or quantum mechanics would need to be revised. Perhaps gravity isn't the ultimate jailer of light in all circumstances. Maybe there are exotic particles or unknown forces that can interact with the event horizon to produce or release light. This would open up entirely new avenues of research, pushing physicists back to the drawing board. This new physics could unlock some of the deepest mysteries of the universe. The information loss paradox might find a resolution if information could be encoded in escaping colours. If black holes could emit distinct colours, it might give us clues about dark matter or dark energy. Perhaps these coloured emissions are a byproduct of interaction. Section 8, Seeing the Unseen, Observing a Multicoloured Universe. Section 9, Conclusion, The Endless Fascination of Cosmic Mysteries. So we return to the reality we know. Black holes are indeed black. Their immense gravitational pull creates an event horizon from which nothing can escape. This is a cornerstone of Einstein's theory of general relativity. The darkness of a black hole is a direct consequence of the laws of physics. Imagining rainbow-coloured black holes pushes our scientific imagination. It challenges our assumptions and opens our minds to new possibilities. The universe might still hold surprises far beyond our current comprehension. New discoveries could reshape our understanding of black holes, light and gravity. Vividly coloured black holes remind us of the universe's wonders. The universe is filled with phenomena that stretch our minds to their limits. From quantum foam to the cosmic web, there is so much to discover. The quest to understand these mysteries drives science forward.